Hi, everybody. Here we are, chapter 4.1. We're ready to look at some more applications of derivatives. Recently we've been looking at what derivatives are, how we find them using product, chain rule, all that good stuff. We've talked about some applications of derivatives. We looked at related rates. And yeah, now we're ready to move on. We're in chapter 4. And we're going to continue talking about derivatives because looking at rates of change still gives us lots of new and interesting powers when we are trying to, in this case, optimize things. Whenever you want something to run efficiently, it's good to know how to maximize and minimize equations. So we're going to use the derivative in order to do that. This first definition about absolute maximum and absolute minimum is pretty self-explanatory. I mean, the absolute maximum is the highest y value that you would get to, and the absolute minimum would be the smallest. And yeah, absolute just means the absolute biggest or smallest in either case. So I don't know there's too much there. I mean, this little definition of showing that any point other than the point in question is less, this definition could be useful maybe down the line, but maybe it's even more useful for the relative maximum. Anyways, that's pretty easy. Let's take a look at some examples of functions and think about some absolute extrema, maximum or minimum, if they exist. Okay, first one is just x squared on the domain from all real numbers. So x squared parabola has a minimum. That minimum would be 0, and it would be at x equals 0. So let's see. Let's go down here. Minimum that equals 0, and it's at x equals 0. Sure. B. Okay, now we're looking at x squared again, but we've got half open, half closed interval here. So if we're thinking about a minimum, we don't really have a minimum. We would always approach 0 from the right on this interval, but we would never get to 0 as a y value or 0 as an x value. So I would say no minimum here, but we do have a maximum when x equals 1. So max is 1 at x equals 1. And I guess for part A, I never said anything about a max, but that parabola is just going to go on forever. So it doesn't have an absolute maximum. It would just go off to infinity. And so we wouldn't name a maximum there. Okay, moving on, part C. We've got x squared. We've got our domain where we're just missing 0 on the interval from -1 to 1. Again, this means that we're not going to have an absolute minimum because that point is left out. But we will have 2 maxes. And that, well, the maximum value will be 1, and that'll be at x equals -1 and x equals 1. But yeah, no minimum. All right, on this one, here we've got the open interval on both sides, meaning that, yeah, 0 is not part of the domain and 1 is not part of the domain. And on an open interval like this, we would be able to approach 0, or we'd be able to approach 1, but we'd never be able to get there. And so we can't label an absolute max or min. So no min or max for part D. And that's one of the reasons why when we look at this extreme value theorem, that it's going to be required to be on a closed interval. Closed interval meaning that the endpoints are included, whereas these endpoints aren't included, and OneNote's not syncing. So I wrote something there. It's not there yet. It'll get there soon. Party. All right. Looking at f of x here, we're on the closed interval from 0 to 1. And this one's a little bit interesting. Maybe I'll maybe do a little drawing up here. What color was I using? I was using orange. All right. So when x equals 0, this function's equal to 1. And again, the thing that I'm drawing is not showing up yet. Hopefully that fixes itself soon. But yeah, the y value is equal to 1. And when we're in between 0 and 1, the y value, there it is. The y value is given to us by 1 over x, which means it's going to be actually some big numbers until we get to the end, when we get to the x value of 1. Oh, actually, but that's closed. I don't know why I drew that open. We're on a closed interval, so yeah, that 1 is included. But yeah, okay. So we have an absolute minimum in 2 places. And the absolute minimum is 1, and that happens at x equals 0 and 1. And for this one, there's not an absolute maximum, because as you approach 0 from the right, that function value would just go off into infinity, and it would not have an absolute maximum. All right, last one. Part F. Here we've got our friend sine of 1 over x on an open interval. And I don't know, maybe again, this one would be a nice one to graph. This is the one where it would look like a sine function, but then get, oh geez, that was really bad. It would go up and down really fast as you approach x equals 0, because this part's going to go off to infinity, and it's just going to go from 1 to -1 a bunch of times. So actually, this would have a minimum at -1. It would have a maximum at 1. And well, those would happen a bunch of times. All right, the extreme value theorem is defined for a continuous function on a closed interval AB. When you have those 2 criteria given to you, you automatically know you're going to attain an absolute maximum and an absolute minimum. Sometimes it might be at the endpoint, so you've always got to check those. But yeah, continuous function on a closed interval, that means that, you know, there's only so much place for it to go. It's going to have an absolute maximum and an absolute minimum. The only way that you could go off to infinity in the y direction is if the function becomes discontinuous. So continuity, closed, both of those are important for this extreme value theorem. The next part's defining relative local extrema. And this inequality looks very similar. Here, we're just going to be interested if there's some point C where all of the other function values are smaller than f of C in some interval, open interval containing C, so it's locally. These ones don't have to be the absolute max for the entire function. Yeah, and I don't know that there's much more to say about that right now. Fermat's theorem is useful. We've got a relative extremum at some point C. If the derivative exists, then that derivative has to be 0. So, yeah, whenever you get a maximum, would be a local maximum. Down here would be a local minimum. Whenever you attain one of these points and the derivative exists, that derivative has to be 0 because generally you're going to be either changing from a positive slope into a negative slope or a negative slope into a positive slope. That can definitely, be circumvented when you're not differentiable. So notice here at x equals c, we're not at a differentiable point. That's more of a cusp where the left-hand limit does not match the right-hand limit for the derivative. And so Fermat's theorem would not necessarily apply there. But the next thing that we're going to look at combines both the points where the derivative doesn't exist and the points where the derivative equals 0 to be called a critical point. So critical points are going to be the things that we're going to want to test. They're going to be our points of interest for testing the derivative to see if something interesting is happening there, at least in terms of maximization or minimization. We're going to look at points where the derivative equals 0 or the derivative doesn't equal, or sorry, isn't defined. So yeah, I mean, critical point, that part's important. This is going to form the basis for the derivative tests that we're going to do in section 4.3. And it's, what we need to look out for when we're finding a schema. Okay. So yeah, if you have a continuous function on a closed interval, like this one is, in order to find maxima and minima, you're going to, here, let me go ahead and I'll write this out. So when continuous on a closed interval, you test the endpoints of the interval for the max min. That's always something you want to be on the lookout for. And then you want to test any critical points. Whoops. Critical points. Yeah, whether that be where the derivative is equal to 0 or where the derivative is undefined. Yeah, and doing that, we will be guaranteed to find the points of interest, our maximum minimums. Okay, let's keep going. I guess this is one little point of caution that Fermat's theorem doesn't say the opposite of what it says. So even if the derivative doesn't exist, it doesn't mean that you're going to be at a maximum or a minimum. It just means that you should test to see whether it's a maximum or minimum. And again, here's where the derivative equals 0, and that's not a local max or a local min. what we're going to be looking for when we're finding, let's say, a local maximum is a positive derivative going to 0 and then going down to a negative derivative. But this one is a positive derivative, goes to 0, and then stays positive. And so that's not, that's not a maximum. Yeah, critical points are more about testing. They're not guaranteed to be maxes or mins. Okay, looking at example 3, we've got a couple examples that we're going to look at here, and then there's one that's going to be actually really challenging. Example number 3, find the absolute extrema of this polynomial on the interval -2 to 3. So we're going to use the ideas that we just talked about. Let's go ahead and test the endpoints. So we would find f of -2. F of -2, 3 times -2 to the 4th minus 4 times -2 to the 3rd minus 12 times -2 squared. All of that ends up equaling 32. Similarly, if we go all the way to the other end of the interval, f of 3 would equal 27 once you plug in 3 everywhere. That's a good thing. For the next part, though, we need to actually take a derivative. So let's, find critical points. So we look at the derivative, which is 12x to the 3rd minus 12x squared minus 24x, according to the power rule 3 times. And here we would set this equal to 0. And solve for the x values where this derivative would equal 0 to find some critical points. There's not going to be any critical points where this derivative doesn't exist because we just got a polynomial. Our only hope this time is to find some places where the slope's equal to 0. On this right-hand side, we could divide everything by 12 and make things simpler. So I'm going to divide everything by 12. And let's pull out a common factor of x so that we're just left with x squared minus x minus 2 times x. And x, if we continue factoring, that would be x minus 2 and x plus 1. And that gives us 3 x values to test, either x equals 0 or x equals 2 or x equals -1. And when we go down here, I put this in here to save time. Right, so these are our critical points. We get different y values for each one of those, but if we're looking for an absolute max and an absolute min, our absolute max would be the biggest number that we see for a y value. So our absolute max happens up there where x equals -2, and our absolute min happens down here where x is equal to -32. Yeah. So really all that is identifying the points that you want to test and then throwing those points into the function, see what y value you get. Cool. Same thing for this one. And I don't know, how about if you guys want to try this on your own, go for it. And I'll write some stuff here. Again, for this one, we want to test the endpoints. F of -1 would be -1 to the 2/3 power which would be 1. And f of 2 would be 2 to the 2/3 power, which would be the cubed root of 4. All right, and so that matches up with what we see on that graph. I guess the final one would be, those are testing the endpoints. We'd need to test our critical points now, or at least find them. So we take the derivative and get 2/3 x to the -1/3 as our derivative. And a critical point here would be 0. Let's think about why. If we rewrite this so that we have 1 over the cube root of x, it becomes more clear that as you approach 0 from the left, you would be approaching -infinity. And when you're approaching 0 from the right, this would be approaching infinity because the denominator of this fraction gets closer and closer to 0, right? And so the derivative at 0 does not exist. And so that's another critical point that we would want to test. So f of 0 in this case will just be 0 to the 2/3 power, or just 0. And if we wanted to test out maximum and minimum, that's what's interesting on that one. Not bad. We can keep going. This one again, it's maybe interesting because you do the power rule. To find the derivative, or you could just multiply x to the 3/5 through. Yeah, I mean, you're gonna get maybe an infinite slope here, which is interesting. You're gonna get a 0 slope here. And you're just gonna test the endpoints as well. So 2 critical points and 2 endpoints. Yeah, I think we're good. I'm actually gonna skip number 5. If you want to come back and do it later, you can. Example 6 is where it's at, though. This is where, we're gonna have to do some thinking. It's actually, an application where we are gonna help this electrical company link their 2 substations together in an efficient means. I love being efficient. Okay, so cables between these 2 substations need to be laid underground and underwater, because they're going to need to go across a river that's about 1 kilometer wide, and the distance along the ground between the substations is about 3 kilometers. Where it gets interesting is that the cost of laying cable underground is cheaper. It's only $30,000 per kilometer, whereas cable underwater is more expensive at $50,000. And our question is, how can this cable be laid in order to minimize cost? And so this actually has a lot to do with the problems that we were just doing, because we're trying to find a maximum or a minimum. Well, we're trying to find a minimum. We don't want to maximize the cost. Maximizing the cost, we could just, I don't know, make the cables do corkscrews, and yeah, it would be ridiculous. We want to minimize the cost for this electric company. And so we actually are on a closed interval here, at least in terms of, I don't know, we've been given some finite distances here. We want to go 1 kilometer in this region and 4 kilometers this way. And so we know that this entire path shouldn't be longer than 4 kilometers. If it's longer than 4 kilometers, we've done something wrong. And so, yeah, we are kind of in a bounded scenario. So we are on a closed interval, and we can talk about that more. And so we're going to be able to find an absolute minimum. One of the first things to do would be, let's test the endpoints. What do the endpoints look like in this scenario? All right, so let me zoom in so I can write neater. Okay. One of our endpoints, or like our extreme scenarios, would be, let's go straight across the water and then straight up. And for reasons that I will explain shortly, well, no, that's fine. We'll just do this. We'll just write it in pink, and the colors will match, and it'll be fine. So in this scenario, where we go straight across and straight up, the cost would be $30,000 times the 3 kilometers plus $50,000 times 1 kilometer. And doing that math, we've got 9,000 plus, or 90,000 plus 50,000, which is 140,000. All right, so that's the cost for the L-shaped route. And it would be the same if you went along the ground over here and across there. Anyways, so the L-shaped route's that way. If we take what maybe we'll call the hypotenuse route, where we would travel the shortest distance possible, because we'd be traveling in a straight line from one substation to the other. The problem is that we would be underwater the entire time. So for this one that maybe we call the hypotenuse, the cost would be 30,000 times 0, because we're not doing anything underground. It's all going to be underwater. And a long ways underwater. In order to find the hypotenuse, we would do 1 squared plus 3 squared equals 10 squared. Well, sorry, equals 10. And then you take the square root of that to get the square root of 10. So this would be 50,000 times the square root of 10, which I think this is going to be 150 some. I typed it in on GeoGebra. Oh, pay no attention to the rest of this. Pay no attention. Yeah, it's going to be 158,113. Ooh, even 88 cents. Okay. Come on. Let me click on one note. Okay. All right, so we've tested the endpoints. in terms of, kind of the longest trip that we could take would be 4 kilometers long in this L shape. And that gives us 140,000. This other one, the long hypotenuse trip, or actually the shorter trip, but all underwater, gives us 158,000 because underwater is not cheap. The thing that's more interesting and probably the most hard part of this problem is finding a critical point to test. Find critical points. And this is actually, kind of interesting because rather than one of these extreme scenarios, we might be able to find a route that goes for a ways in the water, but not necessarily directly across the river, and then goes across land, but maybe there's some optimal path in between the two extremes that we just looked at. And in order to figure this out, we're going to need to give some variables. We're going to need to, make some stuff here. So, all right, I'm going to give this distance the letter G because it's on the ground. And I'm going to give this distance, not the letter V, the letter W because it's in the water. And so, I mean, in order to find the critical points, we're going to need to find a cost function. And right now, the cost would be 30,000 times the ground length plus 50,000 times the water length. Okay, that's nice. But in order to do this well, we're going to need to, we're still in single variable calculus. We need to write this all in terms of one variable. And in order to do that, we can recognize that if this part up here is G and the entire length is 3 kilometers, well, this part down here is going to be 3 minus G. And, this side's still 1 kilometer. So we're going to be able to use this right triangle and calculate W in terms of G. Real quick, sidebar over here. We can use the Pythagorean theorem. W squared equals 1 squared plus 3 minus G squared. And then W just equals the square root of 1 plus 3 minus G squared. And that's fine. So now we can go back and write our cost function as, a function of G, where the 30,000 G part still stays the same, but we get 50,000 times this new way to write W, the square root of 1 plus 3 minus G squared. And yeah, so now these are variable. We can make that go anywhere between 0 and 3. We could test really quick some values of 3 and 0 to make sure they match the things that we looked at the end points, but they will work. Yeah, if you put in 3, this part turns into 1, and we get the same thing as here. And if you make G equal to 0, you get the same thing as you would over here. All right, so now we have a function that we'd like to optimize, and we'd like to find a critical point. And so we take the derivative. Yeah. So power rule just makes that first part 30,000. And then the next part, we've got definitely chain rule kind of thing going on. I'm just going to leave the 50,000 out front. but the derivative of a square root of something is 1 over 2 times the square root of something. So I'm going to just copy this over. And then we need to do the chain rule on this. So we're going to take the derivative of the inside. The one's just a constant, so it goes away. Taking the derivative of 3 minus g squared looks like 2 times 3 minus g, but also times the -1 that's on the inside of the, the 3 minus g. So it's actually a triple layer chain rule there. Goodness. Okay. So in order to get this done now, we need to set all of this equal to 0. And yeah, I think it'll be best for us if we just, let's focus in on the calculations. Sorry if you guys have been squinting this entire time. But yeah, we need to set this equal to 0. Because there's not going to be anywhere where we can make this denominator equal to 0 and make the whole thing undefined. The denominator here is always going to be positive. So we need to, figure out where this could equal 0. All right, so let's just rewrite this. The 2's on the top and bottom will cancel out. I'm going to leave the -1 just hanging out there still, as you will see soon. There's a reason. Okay. Goodness. All right. One zoom out so that we can. All right, have that little bit more room. That -1 is still there. So I could take all of this and put it onto one side or the other side, and that -1 would go away. So, yeah, we could do that. And we could also divide. I'd like to do both of these operations at the same time. All right, imagine that we subtract 30,000 from both sides, and then we divide both sides by -50,000 so that it looks like this. Yeah, that -50,000 is this -1 times the 50,000. That's going to give us a nice 3/5 on the left-hand side. So yeah, we'll go ahead and start writing up here, and we'll box this out so that we're not getting too confused. But yeah, we have 3/5 equals 3 minus g over the square root of 1, 3 minus g squared. Okay. At this point, I would probably cross multiply and write things this way. Yeah, and when you're going through all of the steps, it makes using the calculator really tempting. But it's good to see this at least once. But yeah, we've got a square root on the left-hand side. We need to get rid of that. We're going to square both sides. And get 9 times 1 plus 3 minus g squared equals 25 times 3 minus g squared. So that here we would have 9 plus 9 times 3 minus g squared equals 25. 3 minus g squared. Oh, we are running out of room still. All right, scrolling down, gives us more room. Yeah, we have 9 equals, subtracting over to the other side, 16, 3 minus g squared. And then dividing both sides by 16 gives us 9/16. And then taking the square root of both sides, goodness. I'm running out of room still. I started writing bigger. That's my deal. All right, we're continuing. Square root of both sides. So this side becomes plus or minus 3/4, and this part just becomes 3 minus g. But then we can add and subtract to get g is equal to 3 plus or minus 3/4. Okay, so that means on the ground, we have 2 possible solutions. Well, one of them is going to be impossible because this is our ground length. And if we go 3 plus 3/4 kilometers here, that's going to be longer than 3 kilometers. So that one's just an extraneous solution. But we're really going to be focusing in on the one where it is g is 3 minus 3/4. So it'll be 2.25. We found our g value that we could now put in to our cost function and get the cost at this new critical point. In order to do that, please allow me to put that into the calculator. Here is our cost function. Yeah, notice that when you put in 0, you get the hypotenuse number, and when you put in 3, you get the L-shaped number. Yeah, there's the derivative. And when you put 2.25 in the derivative, you do indeed get 0. So when we put in 2.25 into the original function, c, we get 130,000. So that minimum point would be at 2.25, comma, c of 2.25. It would be this minimum value here. And so the $130,000 option is the cheapest. And yeah, we just saved this contractor at least $10,000 from either one of these, extreme routes. So yeah, actually, our minimum, and I'll write this down in the bottom left-hand corner, the minimum is actually equal to $130,000. And that's at our ground length of 2.25 kilometers. Cool. So there was actually an interesting solution to this one, and not just one of the endpoints. Derivatives are great. A lot of work there, though, to get there. Okay, I think that is the end of 4.1. We're going to move into 4.2. I at least want to talk about Rolle's theorem and maybe introduce the mean value theorem. Sorry if this is getting to be too long. Okay, this next one, the mean value theorem. This is useful because we're going to be able to tell some important facts about the derivative. So an object's instantaneous rate of change without actually ever measuring that instant rate of change. Yeah, you'll see what I mean as we get here. Rolle's theorem. This is the one that leads up to the mean value theorem. It is the version where we have a continuous function on a closed interval again. It's important now that the function is differentiable on the open interval, AB. And the last kind of thing that we need for this theorem to be applicable is the fact that we've got 2 points, A and B. So at the endpoints of this interval, the function value is equal to each other. So average rate of change over this entire interval is 0. What Rolle's theorem says is that there would be at least 1 point, C, inside the open interval where the derivative at that point would be 0. You can see here that since we've got endpoints that are at the exact same y value, we know that somewhere along the line, as long as the function is continuous and it's differentiable on this interval, yeah, at some point, the derivative is going to need to be flat as well. But notice how that breaks when this is not differentiable at all. Like the fact that this is differentiable means that we're going to need to have, if we've got a positive slope at some time, we're going to need to have a negative slope at some time. And in between the positive slope and the negative slope, there's going to be a 0 slope. But for this one, we've got a positive slope and then we've got a negative slope. But since we're not differentiable at this point, we're able to skip over a flat slope. And so, yeah, the differentiable part's important. So that's Rolle's theorem. And the mean value theorem is just a generalization of this, where as Rolle's theorem focuses on having 2 endpoints that are at the exact same y value, so you've got a flat situation, the mean value theorem is going to tilt that. Let's go ahead and just look at this real quick. Zoom out once. Where you've got still 2 endpoints of the interval, but they're not necessarily the same exact y value. But what the mean value theorem says is that for a function that is continuous on a closed interval and it's differentiable on the open interval, there's going to be some point where the derivative, the instantaneous rate of change, equals the average rate of change. So again, you make the average rate of change, as the secant line between the endpoints. But what you know is that somewhere along the curve, the tangent line is going to match that same slope as the average rate of change. So that's pretty cool. Real quick, let's do example number 1 and maybe example number 3. Okay, example number 1, since it follows Rolle's theorem, we're supposed to use Rolle's theorem here somewhere. Let's take a look. Show that the equation has exactly 1 real solution. Okay. So if we're going to use Rolle's theorem, taking the derivative is important. And actually, regardless, taking the derivative is important here because it would be good to know, hey, do we have any maxes or mins to, give us an idea of, does this function change directions in the, or does it always grow, or does it always, decline over time? So, yeah, one of the ways that we could treat this is bring everything over to the left-hand side. And we would be thinking about, where does the left-hand side cross the x-axis? So yeah, where does this function actually equal 0? One of the things that we could do, again, is take the derivative, 5x to the 4th plus 3 is the derivative there, which, notice, since we've got x to the 4th, and that's an even power, this is always going to be positive. And that's actually a big deal. Gosh, how do we use Rolle's theorem? I know it's a proof by contradiction. I guess, in plain English, what we would have here is, all right, so we know our derivative is always going to be positive. That means it's always going to be growing from left to right. And the y-intercept is -2. And so we know that, shortly after the y-intercept, as this thing continues to grow, we're going to cross the x-axis once, and only once, because this will always be positive, and as this is monotonically increasing, there's never going to be any opportunity for the function to go back down and cross the x-axis again. So through explaining, we've shown that this is exactly one row solution. I'm going to punt and go back here to remind myself how Rolle's theorem can play a role. It's not like it's essential, but come on. Okay. All right, zooming in. I love it when the spinny wheel of death stays on this. Anyway, yeah. Oh, okay. So yeah, using a proof by contradiction is not something that is necessarily intuitive, especially if you don't do it very often. Here's the idea. Because we want to show that this has exactly one real solution, what we're going to do is assume, hey, maybe there's two solutions, and then show that that assumption leads to a contradiction. So what we're doing in this sense is saying, if there were two solutions, x equals a and x equals b, of this equation, then we would be able to say that f of a equals 0, and so does f of b. And by Rolle's theorem, there would be some point c where the derivative equals 0, contradicting the fact that we found a derivative that's always positive. So yeah, this is it's a little bit more of a formal argument. Yeah, it's good to see a little proof by contradiction. And sorry that I forgot what I needed to do there. But you assume that there are, you assume that there are two solutions, and then show that that leads to a contradiction where there would have to be some point where the derivative equals 0, because eventually you're going to need to have a negative derivative to come back down to the x-axis. But that's just not the case. Okay. That was example 1. We're totally skipping example 2. And I don't know, if class time needs to be done, we can skip this, but I'll do this, even though I'm feeling like we're probably out of time. Now, this is where we'll pick up. We'll pick up on example 3. So mean value theorem is what we're looking at. And after the mean value theorem, we're going to look at derivative tests. All right, so I'll see you guys tomorrow, and we'll continue talking about this thing. All right, have a great day.